Okay. Yeah, we finally have the right talk. Okay. Well, today there are many, computational methods for, studying properties of materials. I think the well-known methods are right there at the bottom. The DFT methods are based on quantum mechanics. So these methods tend to produce, results that are like very good. Like you can get properties that are very close, to what you would get on experiment. But there are some limitations, though, such as the number of atoms uh, you are able to study, and the the length of the simulations. And of course, there's a lot of technical knowledge required in this type of simulations because you have like so many functionals, and some of them will overestimate certain properties, some will underestimate, some will not be able to calculate certain properties. So for our talk, we're interested on the classical molecular dynamics because they allow us to handle a large number of atoms. And we can run for a longer time scale. Okay, well, the reason we run molecular dynamic simulations at the center is because we can model up to millions of atoms. Though this has previously proven to be, I think a bit too much to run on CHPC, because you need a lot of cores to run a system of 1 million atoms. I think we tried that before. So, well, in classical molecular dynamics, our atoms are typically modeled as charged ions, like cation ions and anions, and then we rely on the classical force fields, to model the interaction between the atoms. And this scheme also, rely on Newton's laws of motion. Okay, so there are, some properties you could get from this, like such as molecular structure, thermal properties and diffusion coefficients of atoms. Okay, so here are some of the classical force fields that can be used in these kinds of simulations. The ones highlighted in yellow are the ones we usually use at the center. Of course, there are other research groups that intensively use the other properties, the other force fields that I did not highlight. So to use this, you typically need some, like for your system, you need some properties from experiments, and then you would feed the parameters of these force fields in such a way that you are able to reproduce, the experimental properties, as close as possible. Okay, of course, we also have 3 body potentials. This can also be used, but they tend to be more expensive than the 2 body potentials. Okay. Okay. So there are methods we have previously used to model potentials. The first one is fitting potentials, manually. Like you just get your laptop, some properties of your system, structural properties, and maybe a Go program, and you try, to brute force, and guess with the values of your parameters for your force fields. And then you have, we have used other methods like FHI aims. FHI aims, I think it's a DFT base code. So what we would do here is calculate total energies, and then we would use some Python scripts, to try to get our force fields. And we also use the media force field optimizer Well, Media is a commercial software that's sold by Materials Design, and the Forcefield Optimizer is a module inside it. So we use this one as well, but it's limited to just optimizing the potential parameters. And finally, we used a program, to just automate the entire process of fitting potentials. This is the recent thing we tried to use to fit potentials. Okay, so here is how you would manually fit your potentials, right? You need to guess the values for your parameters, right? And then you'd run it to geometry optimization, and that gives you, your lattice parameters and your properties, and then you compare them with experiment. And if it's not possible to improve them anymore, you can take them as your final, set of parameters. If not, you continue to improve them. Yeah, but the question here has been like, how do you, optimally adjust these parameters? Okay, so this is typically what you need to do this fit. This is a typical gulp input file. You need your, cell parameters, the positions of your atoms, and then you need your experimental properties. If you cannot get these, nowadays people will obtain them from DFT calculations. In some cases, they tend to be very, very close to experiment. And then you need your potentials. So you can just set like values of 1 for the potentials you are going to fit. Okay, not in this case. I think in this case you need to just guess what they are. Run that command over there, and then hopefully that will be the only time you run a fitting calculations, and then you will get results. Okay, so if your initial parameters, let's say they're on that red dot there on the potential energy surface, then what the gulp will do, it will probably find the potential parameters at a global minimum, and you will be done with your fitting sessions. I think you will have won the lottery, and you will probably be one of the most lucky people in the world. But most of the time you get the purple dot. And then if you try to this kind of calculation, you don't get optimal parameters. So the idea has been to try to get to the global minima, like closer to the global minima as possible, and then run the previous calculation to get your optimal parameters. So one other method was to use FHI aims and Python. So this is a case where we had, I think it was rutile TiO2, and then we would replace half of the titanium ions with manganese. Run a geometry optimization, on custom, get our properties, and then we would attempt to get the titanium, manganese, interatomic potentials. So you typically take like two atoms, 1 titanium, 1 manganese, and then you put them, let's say at 1.5 angstroms. You run your FHI aims, geometry optimization. Okay, you record your total energy, and then you gradually move the 2 atoms apart each time you calculate your total energy. And then you take the total energy, of the last calculation, and then you subtract it from all the other total energies. And then that enables you to have that plot over there. So this plot resembles a Morse potential or a Buckingham potential. So you can fit your Morse potential parameters or Buckingham potential parameters, to this. So we fitted the Buckingham potential parameters. So we realized that the potentials, it needs to be like further refined. I think the A parameter was underestimated, the C parameter was overestimated. I think the rho was very close. So this saved us a lot of time. So we only have to optimize the other 2 parameters, which which didn't take, I think, a day. Okay, so another method we used was the media force field optimizer. So in this, with this, you start with your system, and then you have to run a DFT geometry optimization. Of course, knowledge of DFT is required here, so you don't get incorrect results. Afterwards, you need to run molecular dynamic simulation to create, some trajectory files. So you run this at different temperatures. And then afterwards, you take your trajectory file, and then you would take some existing potentials you had, and then you try to optimize them. So yes, I found out that this method requires one to, like it is a steep learning curve, you need to learn a lot of things on the DFT side, and also on how the force field optimizer work. And the results are not that particularly impressive. Okay, so for this session, I think we will be looking at how to fit potentials now with the program we developed. I named it NIFIT, like Mwepe Intuitive Interatomic Potential Feeding Program. So this program was developed using C++ in June this year. So so it's able to optimize like existing force fields. Like you can just get some potentials from papers, from journal articles, and then you can use this and then try to optimize them. Or you can just feed your own potentials from scratch. So the program is currently able to handle the Buckingham force fields. Of course, there are other features that are in development, like support for other potentials like Morse and three-body. Okay, this is NIFID, well, inside. So it was made using C++. So we try to use C++ libraries that are typically used in data encryption. So like the C++ random device, the Masonite twistor engine, the uniform number, like integer distribution. Well, the reason is that if you're fitting like 6 parameters concurrently, it's very difficult for a human to do it, and you have a lot of possibilities, probably trillion sets of these potentials. So we want to sample each parameter combinations like evenly, so which is why we use this approach. Yeah, and the program also support OpenMPI, which means it can take advantage of the large number of cores at the center of high performance computing. Okay, so the algorithm used is typically this, like you need to guess your initial parameter sets, and then you run a geometry optimization, right? So this gives you your properties, and then you use your properties to calculate a variable we call a score. This can be, by the way, the sum of squares, right? If that value is not too large, you can proceed with the next step. The reason you need these values to be like small is that if it's too large, the program will take a long time optimizing those parameter sets. So it's better if you choose the value that's not that large. Okay, and then after you get your decent initial parameters, and then you just optimize them. Like you take each parameter and then you optimize it. Like you increment it by some value. Run your geometry optimization. Okay, reset, and then you decrement it, and then you run your geometry optimization. Right? You do this for all the parameters, and then you just compare which one gave the best score. Then you take that parameter, and then you take that parameter. Then you need to update your initial parameter set with it. If after this process you have no improvement, then you can just save your parameter set, and then continue with the next generation of new potential parameter set. Okay, so there are two methods used in this program, like the hard algorithm and the soft algorithm. So the hard algorithm is typically what you do is, yes, you need to guess your parameters and geometry optimizations, and then you do all these increments and decrements again, and then you get scores for all your parameters, right? So the one that gives you the best improvement, you take that. Like if you had incremented that parameter, you increment it until you don't get any more improvements, and then afterwards you update your potential parameters with that value, and then you continue again with your increments and decrements. Right, and the other one is a soft method. Here you only need to, it's the same process, but you only need to increment once. Right. Okay. So the program is able to, by the way, optimize existing potentials. These are the results where we try to optimize some lithium oxide potentials. So I think the column in red is experimental values, like experimental properties we are comparing to. So, well, in this case, the program did not do well in terms of lattice parameters. Well, had we put a bit more effort into it, I think we could have gotten better lattice parameters. But overall, it did actually show some improvement. And then we got this when we implemented, well, the soft method. And this is a case where we try to match our, like the lattice parameters from our optimized potentials and the potentials we're optimizing. So it's evident here that the results we got were like they were improved, I think, a lot, except I think for the static dielectric constant. Let me see. Or even that I think was improved. Yeah. So on average, yeah, this program was able to do this. And these calculations, by the way, they don't take long. And this was actually run on my laptop. Okay. So another method is just feed this potentials from scratch. So what you typically need to do this, it's a gulp input file with information about your structure and your properties. And okay, and you can set the values of 1 for the potentials you are going to feed, because it's not important what they are initially. Okay, so, and you also need a settings file to do this. You need to specify how many, initial parameter guesses you're going to run, and on the highlighted region there, I think the 111, this is where you specify the parameters you're going to feed. In this case, it's we're feeding parameters for the backing potentials. So 111 represent A, rho, and C for both interactions, and then you specify the range for the values of your potential parameters. And then one other important thing is debug. If you're starting to fit, you need to set it to 1. It will show you the scores for your potentials. Like if you get scores that are like 900, that could mean that there's something wrong with your gulp input file, or maybe your properties are not that good or are incorrect. We once got values like that when we used properties for a different system. And of course, you can actually set weights if perhaps one lattice parameter is not giving the correct value. Okay, and you also need a bash script. This is in case you want to run this at the center of high performance computing. So this is what you need. You can run this on any number of processors. We ran this on 24 cores on Lengau, I think on the SMPQ. And the calculation took like 5 days, but of course, within the first few minutes, we already had some results that looked promising. Okay, so these are the results we got after running this program for 5 days. So we got like about 2 million potential parameter sets. So what we did is we sorted them according to the score, like from lowest to highest. So the best ones had the lowest score. So so what's interesting for LITO is that For set 1, the lattice parameters were not very good, but the other properties were very good, and that includes the static dielectric constants, right? So set 5, it's a case where now we try to get good lattice parameters, but and then in turn we sacrifice the static dielectric constants. So I would actually use set 5, I think, for simulations. Okay, well, in conclusion, the program has simplified the process of fitting interthermic potentials. So we typically used to take months to fit these potentials. Now, I think 1 week is usually enough to get like very, very good potentials. I think if you look at is it set 5, some of the properties are like very close to experimental values. Like you have percentage differences that are just less than 1. And usually this is not it's not humanly possible to get such potentials when you feed manually. Okay, so this program is able to run a CHPC and desktop PC, like on a Windows machine. What is that? Yeah, and I would like to thank CHPC, because part of this program was developed on CHPC systems using the software development tools they have on the system, and it was also tested on CHPC. And I would like to thank the University of Limpopo and the Materials Modeling Center. Thank you.
Thank you very much. Thank you. With that, we are at the end of the session, and I would like to open the question.